diagonal will cross. This is what it says. And then this will have a center of gravity. You have to be careful here because you can find the center of gravity of this rectangle, but when you get the coordinates, you have to add the 20 here, and then we have to be careful. Okay. So it will, what would be the distance from here to here? Because this total is 100, this is 20. Okay. So this is going to be what? From here to here, it will be 80, isn't it? So this will be half of that, then it's going to be 40 from here to here. You see that? But what will be the coordinate now? I had to add the 20 because I had to start from the 0, 0. You understand that? So the coordinate of this will be 20 plus 20, right? Which will be 4. So this will be x coordinate will be 4. What? Wait a second. This is a 40 plus 20, right? 60. Then what will be my y coordinate? If this is 40, then it will be half of that. So that should be 20. So important thing is to write down these coordinates properly. Once you do that, then this can be fairly simple. Okay. So now what do I have actually? I have two masses, one at here and then the other one at here. So this whole picture becomes a point mass here. This whole rectangle becomes a point mass. Okay. So two masses. So that means something similar to what I started with, right? Yeah. Shane? Okay. So this is from here to here. What is this length? Huh? How did the 80 come about? 100 minus the 20. So this is 80. Okay. So this will be right in the middle. So from here to here, it will be 40, right? But I had to add the 20 to get the coordinate of that. Okay. We deal with the coordinates, not the lengths and stuff. Okay. Because that's for this x and the y. So those are the coordinates. All right. So I have two masses now. One at here and one here. Okay. Now the question is, what are these masses? I have a sheet here. Okay. The mass of the sheet depends on what? Amount of material, right? It's a uniform sheet made of the same material. So what would be the mass of some rectangle proportional? If you were to really calculate the mass, what should you do? You have this, let's say, and then has some thickness. So let's say this is H, this is W, and the thickness is T. To find the mass, what you have to do? Get the cross-sectional area, then multiply by the thickness, right? So it will be H, W, T. That will be the volume of this block, right? Then what you have to do? Multiply by density to find the mass, right? Remember, density was equal to what? D was equal to mass over volume, right? Density is usually written as rho. So to find the mass, what you have to do? Multiply the density by the volume. So we just found the volume here. This is your volume. Then multiply by the density to get the mass. Okay. So, and then this is made of the same two materials. So this is going to be what? Different H, T. T is the same because same thickness, because you take the same material sheet and cut off. Okay. Only difference would be for that would be H and W, right? This is that. This will have a different H, it will have a different W. But the T is the same. It's the same sheet you cut out, different sheets. So that will have a different H and a W, but the T is the same. Same row. So what are the ratios of this mass is going to be? The mass will be proportional to what basically? Say that again? Not just the height. Height is part of it. Isn't that the area of the sheet? You take a large area of the sheet compared to a small area, what larger one will have more mass, right? Okay. So the one that really determines the mass is not you really don't have to calculate the mass per se. You can approximate the mass, you can proportionate the mass to what? The cross-sectional area. So if I find the area of this one rectangle, and area of this rectangle, then I can use that as the proportional masses. Why? Once you have the area here, what do I have to do here? Multiply by the thickness and the density to get the mass, right? Well, if I have the area of this one, what do I have to do? Multiply by the thickness and the density. So same thing comes into play here. D and the rho comes into both masses. So I really don't have to worry about these guys here. Then all I had to worry about is the cross sectional area. Okay, they're not really cross section. You can call it just the area. All right. So what will be the proportionate mass for this one then? 20 times 200, right? That's the area of this rectangle, right? So this will be 20 times 200. Then what will be the mass of this one? Proportionate mass of that. This side was 80 times 4. You see that? That's what we are going to use. Why is that? Because you see the mass at the top, mass at the bottom, right? So this mass will have a area times the thickness times the density, right? This one will have an area times the thickness times the density. So the thickness and the densities will cancel. That's what I said. You really don't have to calculate the true mass. You can just leave with the area. Okay. Area. All right. So now I'm going to calculate the x bar CG. That's the x coordinate of my center of gravity. For this one, what do I have to do? M1 x1 plus M2 x2. I have only two masses here, right? I have this mass and this mass. You see that? So my formula that n formula boils down to only two. It limits to two. What is my M1? Let's call this one my M1. This is M2. Now M1 would be what? It is proportional to the area, which is what? 20 times 200.
So each time you can get the area of each of those respective rectangles, and that'll be the mass.
That will be the proportionate. That will be proportional to the mass.
Okay.
You read? Huh?
Always.
Always.
Okay.
No, the question has to say it's made from uniform, cross-sectional material and the same material. Okay, because one part cannot be, this part cannot be steel, the bottom part cannot be wood or something. It has to be steel right throughout everything. Because this has to be steel, this has to be steel. Otherwise, two different masses, right? Because the densities are different. It has to be same cross-section. If the cross-section is changing, you cannot do that either. Understand that? Because this is twice as thick as this one, then you have to account for the thickness. This you took the same sheet and cut out a bigger rectangle and a smaller rectangle. Then the cross-sectional, the thickness is going to be the same, material is the same, so that's when you just compare the areas.
So then on the final, are you going to give, do you think, probably uniform?
Yeah, most probably it will be uniform material, a sheet made of uniform material that has the same thickness. So all you have to do is to get the areas. So this is M1 here. What is X1 now? That is the X component of your center of gravity, right? Which is 10 here. This is it. We already marked. So this is the area. This is, I'm going to write it as A1. This is X1 plus. Then I have to get the mass of this one. So that means area 2, right? Don't get confused with the center of gravities and the areas. Area is just the length times the width. Okay, center of gravity is the distance from the x-axis and distance from the y-axis. Okay? So in this one, it's going to be what? 80 times? 80 times 4. This is A2 times, what's my x2? x2 is 60. I already marked those. Divided by the total mass. All I have to do is to add the A1 and A2 here, right? Which is what? 20 times 200 plus 80 times. Put it in your calculator, and I'm going to do some simplifications here. Then I can divide each and every term by 2 to get rid of this guy. This is gone, this is gone. And then when I divide by 2, I get 2 here, 2 here. Now I can divide, what else? I can divide by another 4 probably, but do put it in a calculator and tell me what it's like. 33.2? 32.2. 32.2? And this in centimeters, so this is going to be coming in centimeters as well. Okay, this is one time you don't have to really convert everything to meters. You can leave it centimeters and you can leave it with grams. Okay. That's XCG. You're not done. Remember that you have 2 components. YCG would be M1 Y1 plus M2 Y2 divided by M1 plus M2. And now again, these things are going to repeat. You know what I mean? This A1 and A2 are going to repeat. The same thing comes at the bottom. Only difference would be X1. In place of X1, you'll have Y1. Here X2. In place of X2, you have Y2. That's all. So this can be 20 times 2. Y1 would be what? 100. So this is nothing other than X1 Y1. This is X2 Y2. And then plus A2 is going to be same thing, 80 times 40. Times what is your Y2 going to be? 20, right? The whole thing is divided by the same denominator. How much is this? So now we can write center of gravity is equal to what? 32.2 comma 64.2 centimeters. These are the coordinates of your x CG comma y CG. So this means the x coordinate of your center of gravity, y coordinate of center of gravity. Actually, strictly speaking, I didn't do the sig figs right. You can leave it to 1 sig fig, because these are going to be just 2 sig figs. These are 2 sig figs.
But you keep it like y or x and y components.
Yeah, that's fine. You need to leave the coordinates. That's all. X and y coordinates.
So you use those coordinates to figure out exactly what's the root.
So the meaning of that is then I had to come to 32.2 on the x-axis, right? Along this, and then go up 64 point something. So you can appreciate now your center of gravity is not even on the body. That's a key thing. Yes, it's possible. Okay. How can that be? It should be, strictly speaking, it should be on a line where these two are joined together. It has to lie on this line. Because if you have 2 masses like here, let's say you have one ball here and a tennis ball and a ping pong ball, the center of gravity of that has to be on the line that's being connected, right?
So it's basically telling you, like, if you build a building, that you would have to create some a pillar or something like that.
Yeah, actually, strictly speaking, as you said, you put a weightless rod, and you can balance it right on that point, on that rod. That's the meaning. Okay, it's not horizontally; it has to be coming down like that, and
That's what you're saying. It has to be like a V.
If like a V, yeah, something like this. You have a rod connecting here, and then you can balance it right here. That's the meaning. Yep.
Okay, so it'll be exactly in the center of those 2 coordinates.
What do you mean center? Coordinates are points on the space,
Right. Yeah. So like you've got like the 10 and 100 there. And
No, because the masses are different. Therefore, it will be closer to. It has along the line. That's all. Not at the center, no, no. It all depends on the mass because if this guy is heavy compared to this guy, your center of gravity is going to favor this one, closer to this one. It makes sense, right? In the heavier one and a lighter one, you cannot balance it right in the middle. It's going to just tip like this, right? That's what you did in the lab. It has to be closer to that so that the heavy one, the lighter one can balance the heavy. It's like a theta target. Yep. The body, yeah, it's possible. That's what the whole point of this exercise. There are students saying that the center of gravity has to lie on the body. No, we just found out it can lie outside.
Answer question.
Yeah.
How much you fall to fall? Because see that was like a ceiling, right? That L is there. So it's a roof, right? That roof, that L. Yeah. Say that was a yeah.
Yeah.
So if you put pillars at the M2 and M1, that would still hold it up.
Oh yeah.
It's on the line.
Yeah.
On the line, right?
Yeah. You can have a support right at M1 and you can keep it horizontal like the L like this and keep an M1 support the M2. So it's not going to fall out. But if you are different place, then it's going to topple to one side. All right. So make sure you know how to handle a situation like that, or else something like this. You know what I mean? Some ladle like thing.
So that's the same thing.
Same concept, you create a, rectangle here. This one will be straight, center of mass will be here, center of mass will be here. If it is uniform and, equal in distances, so your center of gravity has to lie somewhere in between on that. Of course, closer to this one because this is a large area, more weight. Okay? Or else I can give something like this, non-regular shape. It's big to one side. So now center of mass is here, center of mass is here, so it's going to lie somewhere. Don't worry about where it really lies, just calculate the x and the y and tell me what that's all. All right, that could be one part of a question on the final. And okay, the next one is the relationship between the torque and the angular acceleration. If you recall, what was the relationship between force and linear acceleration? Well, there was a law involved in that, right? Force and linear acceleration. No. Force and linear acceleration. It has nothing to do with rotation. Say that again? Exactly, Newton's second law. Okay. So similar to that, remember that everything has to be translated to rotational now, right? So let's start with Newton's second law for translational motion. Translational means it's going in a straight line. And then do the translation for that law into rotation. This is what we have. Sigma F was equal to ma, right? That was Newton's. Now I'm going to translate this to rotational stuff. Okay? What's the equivalent of force in rotational terms? Remember, because to get something moving, I have to push it, right? Apply a force. Now I have a disk, I want to rotate that. What do I have to do? I have to apply a torque, right? So this is going to be tau. Sigma tau should be equal to what? In place of mass, what comes in? Inertia. And then in place of A, this is the linear acceleration. It should be up, angular. So this can be vector. So that's how you translate this linear equation into rotation. Now let's take a instant example. I have a pulley here. There's a mass of m and a radius r. Now, I have one mass hanging here, the other mass hanging here. Okay, there was a name for this kind of thing. We call it a certain machine. What machine is this? Atwood machine. Okay, this is called the Atwood machine. Okay? And now, if you look at it, let's say that you had a higher mass here and a lower mass here. Remember when we neglected the mass of the pulley and neglected friction, what happened to the tension? Tension was all right through, it was the same value, right? But in real life, there's nothing called a massless pulley, right? No matter how small it is, it will have some mass, right? It's a material, made of material. Okay? So therefore, it will have some mass, it has some, some finite radius here. So therefore, what happens is one will have a larger T, this is T1, this is T. The tension won't be the same. This is the true real life situation. The other one was an ideal situation when we took the tension to be, the same everywhere. Now, let's say T1 is larger than T. What will happen to this pulley? It's going to rotate like this, right? This one is pulling more than this one, so it's going to rotate like this. Okay. Now, let's analyze that situation. So that we have rotation, so that means what? We have to use Newton's, the translated Newton's, right, into rotation. So sigma tau should be equal to I times tau. What is tau? That's the torque, right? How do you find the torque? Jenna? No. How do you find the torque? What's the definition of torque? Anybody else?
Position. Just apply force from the position vector?
Yeah, force times the perpendicular distance to the force, right? We did this in the lab. Okay. Now I have a force here. This is the pivot point, right? Because that is where the pin is. It can rotate about that pivot. You see that? That's goes through the center of the circle and the center of the pulley. So this is your pivot point. So what do I have to do? I have to multiply this force by this perpendicular distance, which is what? Radius. Okay. And before we go anywhere, I had to take a preferred direction. Let's say that I'm going to use this thing clockwise. Okay. This guy creates a clockwise torque counterclockwise torque. Clockwise, isn't it? Because this is the pulley, so you can keep your pivot here, and this is the force. It's going to rotate in this direction, right? This guy. So that one is going to be positive because I took my preferred direction to be clockwise as well. What is the value of that torque? Force is how much? T1. What's the perpendicular distance to that? R. So this is going to be T1 R. Understand? All right. Now I am here. Now this guy is pulling this way. Oops. It will be negative, right? It is like this, pulling this way. That's going to rotate it counterclockwise. My preferred direction is clockwise. So that guy is negative. What is the value? Force is T2. What's the perpendicular distance to that? I again, radius. Okay. T2. So this is my net torque in that direction. Okay. That should be equal to what? I times alpha. What is the I for a pulley? What can you approximate the pulley to be? A solid disc. It has a little tiny groove at the top, right? You know what I mean? Other than that, this is what a pulley is, right? Groove for the string to go in. And so you can approximate this to be a solid disc. Okay. So what is the I for a solid disc? It's on page, what was it? 251. So this is the case here, solid disc. Okay, it's going to be 1/2 m r squared. So I can write my I to be what? 1/2 mass is m and r squared. So this is nothing other than 1. Now alpha is the unknown. I'm trying to find. Makes sense? So if I were to give a situation like this and given this force is this much, that force is this much, mass of the pulley is this, the radius of the pulley is that, you should be able to tell me what my alpha is. What does that mean? There is a net torque here, so that means there's an angular acceleration. So as time goes on, what's going to happen to this pulley? Keeps on rotating faster and faster, right? Because of the angular acceleration. Are you alright? Because the angular acceleration is going to keep on rotating faster and faster. Okay? So I can give you a situation like this and say this starts from rest and ask you to find the speed of this thing, rotational speed, after 5 seconds. How can you do that? First, what you have to do, find your alpha using the same principle. I give you T1, T2, mass, and R. Find your alpha. Then what do you do? You use a kinematic equations because you know your alpha. What is your omega I? It starts from rest. Omega I is 0. Okay? And your alpha you just found out, calculated from this. Okay? And then the question is, what is your omega F? And you're given T is equal to 5 seconds or whatever. You should be able to. Be ready for something like that. And be prepared. I wouldn't say ready, but be prepared for something like that.
So you give us alpha without choosing?
No, I won't give you alpha. You better calculate the alpha.
So you're giving us everything else?
I will give you T1, T2, M, and the R.
And then we put it into that equation.
Equation and the R.
Okay.
And this equation won't be given. The only thing that will be given is this. You should be able to apply that and this equation to this situation. Okay.
But we are going to have this big,
Say that again.
big measures.
I will scan this page and this will be part of your file. Okay, this page will be part of your file. In a situation like this, what would be the talk of this? Let's say that you have like a spool of thread, big spool of thread, okay? And then you're pulling that one, the loose end with a T. What are you doing to this spool? Everybody understand? You know what I mean? I have a big spool of thread. I'm pulling the thread. I'm unwinding the thread from the spool. Okay? What will happen to this spool? It's gonna, rotate, right? It could start from rest and it's gonna rotate. What am I applying? I'm applying a force and I have a perpendicular distance to that. As Eric said, I'm applying a torque to this, right? So what will happen to this spool? It will have an angular acceleration. It will have some alpha. In this case, what is the torque that is applied here? P times whatever the radius is. There's no other force here, just one force. Okay? There were two forces, so you have to get the net torque there. Here only one force applies to the torque. Okay? Get that torque and then that should be equal to what? I times alpha. How do you find the I here? Again, mass 1/2 mass times the radius. Okay? And then get your alpha. Once you have the alpha, I can ask you, how many turns it will do, in 10 seconds or whatever. It just becomes a kinematic, rotational kinematic problem. First step is to find out. Okay? Be ready for something. I keep saying ready, be prepared. It doesn't mean this will be there. There's a detailed example here, but do not waste your time on this. But somebody like our young man can appreciate something like this. But I won't have this on the test. It's too much. That is on 256. But from an exam point of view, do not waste your time. But do you see that T2 and T1 are different here on the pulley? That is because the pulley has some specific mass. Now you will appreciate why we, assume that there was pulley was massless and the, frictionless. Okay. Moment you put the mass, what will happen? The tensions are going to be different on either side. Okay. That was the whole reason. We talked about angular momentum in the lab. What is all you have to know is this guy here, I1 omega, I omega I is equal to I final omega. We did this in the mass. So that was the skater, going into a spin. Okay. That's the whole concept. It's all explained here in the next pages. And then that concludes this section. I forgot to mention something, an application about circular motion. This is strictly not centrifuge, but related to centrifuge. You have, I'm sure some of you have done this in your chem or bio lab. You put some stuff into a beaker, and you put that beaker onto a rotating table to mix things up, right? What will happen? It'll just have a concave. So this is your beaker. It'll be something like that, right? Form a meniscus like that. Now, if you have heavier particle and lighter particles in here, heavier particles are going to go to the wall, lighter particles are going to be close to the center. Okay? That's one way to separate things, heavy particles from lighter particles. Okay? That's what they do in centrifuges, like to extract uranium out of that. Uranium is a heavier thing, so you spin it and get the outside part, and then you have to keep on spinning it in several, step by step, in several centrifuges to get atomic grade uranium. That's what the uranium is atomic grade. Rest of the world is trying to stop. So that's one. There was an application of this. Because some parents want to have a boy or a girl, specific, gender. Okay. So what there was a method they did was, take the sperm of the father and then put it into rotation like this, and the X chromosome and the Y chromosome, are slightly different in masses. They say. I'm not sure how true that is. So let's say the X chromosome, the male one is lighter than the Y. Male is X, right? Isn't it? Y? I'm sorry. Yeah, I do not remember. Okay, so male is Y, X is female is X. So the males are going to be outside. No, male is going to be lighter, so it can be in the middle. So the females are going to be on the edge. Okay. So what you do is you rotate it and suck out the middle part. And then you artificially inseminate the female with that. So you have a higher probability of getting a male if you want. If you want a female, you go to the wall and extract that out. And you do this in farms mainly because especially for cows. You don't want a bull, right? You need only one bull, and that can breed the entire army of cows, right? It's a cool job, but you need only one bull for the whole, to fertilize the whole females in the farm. But only thing is, but if you get males, all you can do is to use it for stud purposes and then for meat. The cows will give the meat and the calves, and then at the end you can use it for meat as well. So a female cow is worth 10 times more than a male cow. So they want to breed, selective breeding of females in the farm than males, so that they use this kind of thing, for rabbits and sheep and all that. I never set it up, but in the sum it's difficult to do that. These are the things that students talk about in the practical applications. I wanted to do that, but I never got around to it. So that 25 points for your practical application, since we never did any one. What should I do with that? I should take out the 25, right?
No, you should give us 25 because we work hard.
Yeah.
You should give all us 25.
All right, everybody gets 25 points. So.
Thank you.
Yeah, it's my fault. If I told you I pay for my sins, so if I didn't do something right, I won't hold you responsible. I take the responsibility.
On Monday, we can get the rest of our quizzes back.
What are the quizzes? My main core idea is to get the exam back. That it's gonna take me some time, and you'll probably won't get back the formal lab because that's the most time-consuming one. So you'll see the grade on the formal lab, the report on the canvas. That's basically. But if you need to collect any of that, you'll have to come and talk to me when I'm teaching in fall. I'll teach Monday, Wednesday, and Fridays. All right, thermal physics. There could be a question on this also. This will be the last section we'll be talking. Last couple of sections. Temperature. What's the definition of temperature? You have seen this temperature thing before. How do you define temperature? Temperature is a measure of what? Heat. Energy. Yes, it's a measure of energy. What energy is it? Tell me in something that you already know. Kinetic energy. Okay. Thermal energy is the average of, there are a whole bunch of particles. Remember just, if you have particles, they are not just staying there, like if you take a bath of water, they're just going in Brownian motion, right? Random motion. No particle is going to stay somewhere unless it's a solid, okay? So liquid and gases, they will be in Brownian motion, okay? And some particles will be at a higher velocity than the others. So when you average all the velocities of the particles, so temperature is an indication of that average velocity. So if you heat it up, let's say that you take the water and heat it up, what's going to happen now? The velocities of this motion are going to be higher, right? So what does that mean? Temperature is going to go. Okay? That's the meaning. So temperature is nothing other than kind of an indication of the kinetic energy that you have for that particular mass that you're interested in. Okay? Even for a solid, when you heat it up, solids, they don't go from one place to the other. They just vibrate in place. You know what I mean? They're not free to go. But even that vibration are going to be a lot severe than before. Okay, so you average, speeds of vibration is going to be high. Okay? So it's the same concept. So temperature is nothing other than a measure of the kinetic energy, average kinetic energy. Then we talked about in this section, they talk about the different temperature scales, which we already did. Celsius, Fahrenheit, and then what else? We did Kelvin. Okay. And you know how to convert from one to the other. I tested that on the first test. So yeah, that still holds. You are still responsible for that. Do not worry about 10.3. That's the thermal expansion. If you get into engineering, you'll talk about that. Forget about 10.4, macroscopic ideal gas. You'll be talking about the kinetic theory of gases and all that in an engineering course or advanced physics class. So out of chapter 10, all you have to do is to know the different temperature, scales you use, measurements like Celsius, Fahrenheit, and then Kelvin, how to convert from one to the other, and just have an idea of what temperature is a measurement of average. Say that again? No, I'll give you the conversions. Yes. Same equation that was on first test, will be there. So it will be, the equations will be just taken from each test and added, one on top of the other. And then I'll have the equations for the last few chapters that we're talking about, like the rotational dynamics, what the I's are, and then what's the definition of a rotational kinetic energy, 1/2 I omega squared, that kind of stuff.
So the only additional information is in chapter 8 and then
Chapter 8, there are two sections of chapter 10, and then we go into chapter 11. There could be a question based on this. Units of heat. So, this is chapter 11.1. Heat is an energy. Okay, there are different forms of energy, right? Mechanical energy. Mechanical energy can be consisting of what? Potential and kinetic energy. Okay. Then there is magnetic energy. It's called electromagnetic energy. Then heat, sound, light. You know what I mean? Those chemical energy. Those are forms of energy. We talked about that before. Okay. So there are two types of units for heat measurement. One is calorie, the other one is joules. Because remember, it's still energy, right? So you can use joules as to measure heat energy. Okay. The definition of energy is this. Let's go to this equation here. This is a good. This will be given on the test. Q is the heat amount of the amount of heat energy that crosses M times C times delta. M is the mass, C is called the specific heat. So definition of specific heat, so that is C specific heat, and then delta T is the difference. This is specific.
so is specific heat something that we'll calculate or is it a coefficient that
Usually specific heat is different. Delta T is the temperature difference. That means T final minus T. I use it slightly differently in this case, and this is mass. I use this as change in temperature. That's the amount of heat some object can have if you were to compare from the absolute zero. So that's the amount of when you go higher and higher temperatures, and you can assume that you can get an idea about how much heat energy is stored in now. So let's talk about the units here. Let's go into SI. In SI, energy is measured in what? Joules. So this side will be joules, and then the units of this side will be joules. Mass is in kilogram, right? And delta T would be in SI. Usually Kelvin, right? Delta T is in Kelvin, but you know what I mean. So this will be. Your time will be lowercase t. This is Kelvin, and then therefore specific heat should be what? What should be the units of specific heat? C. Joules per kilogram per degree per Kelvin, right? Yeah, that's how it is. Okay. That is SI. Okay. But sometimes you can have mismatched things. You can have give the temperature in degrees C. It all depends on the units of your specific heat. If the specific heat is given joules per kilogram per Celsius, then you have to use the Celsius, not difference in temperature in Celsius. Okay, it all depends on your specific heat. And so that is in SI. Okay, if you were to use British system, this is measured in. There's another system to measure this is in calories. What would be the? It will be grams. Then the specific heat will be. We'll talk about that, and then the temperature difference is usually in degrees. So now the specific heat unit will be what? Calories per gram per degree Celsius. Okay. When you work out a problem, you'll understand a little better how to use that specific heat thing. If you look at the table on page 365, these are specific heats for different objects, different materials. Aluminum, they have given the specific heat in joules per kilogram per degree C. You see that? Joules per kilogram per degree C. So not Kelvin here. You know, if it is strictly SI, it should be Kelvin, but you can have mismatch, you know what I mean?
You can't do the algebra with it.
No, then you have to use the temperature difference in Celsius.
Yeah.
Because this is Celsius, it has to cancel out, you know. Okay. So you have to look at what is given in your specific heat, what is the units, and then pick the temperature, you know what I mean, according. Okay. This one is given in calories per gram per degree Celsius. So most common temperature would be in Celsius, you know, and that's the most common. All the SI is degree, like kelvins, you know. Okay. So it will be given. So you will be using temperature differences in Celsius instead of kelvins. And there was an 1 calorie is equal to this many joules. Okay. The meaning of a calorie is if you take 1 gram of water and then raise the temperature of that by 1 degree Celsius. Okay, that is what the definition of calorie is. All right. So now let's think about a situation where you have this. Let me give us an example. Let's look at this one here. 125 gram block of unknown substance with temperature of 90 degrees C is placed in a styrofoam cup containing this many grams of water at this. Okay, this many kilograms of water. The system reaches equilibrium temperature of 22.4. Now this is what happens. If you look at this, this block is at 90 degrees C. Water is at 20 degrees C. That is the room temperature, about 20 degrees C. Take it to it. Okay. So now what happens is what? You have a hot block. You put it into this cold, comparatively cold water. Okay. What will happen to the block? It's gonna get colder, right? The temperature is gonna drop. What's gonna happen to the temperature of the water? It's gonna get warm. Okay. So the whole idea of this is where the heat is transferring from the block to the water. Heat always transfers from the hot object to the lighter, to the cold object. Okay. When you have temperature difference, heat will transfer from the hotter object to the colder one, and then eventually we'll have the same temperature of all objects. Okay. So it's like socialism, take the money from the rich, give it to the poor, everyone will be at some point. Okay. So whole whole the universe is like that. You have higher potential energy that gets converted to kinetic energy. Okay. So you're trying to minimize your total energy in that situation. That's the universal.
Huh? You said when they do even out, that's equilibrium.
Yes, eventually the temperatures will come to equilibrium. So the block will have the same temperature as the water. So they won't, at that point, what will happen? There is no heat is transferring anymore. There is nothing called colder, nothing called hotter, because everything is the same temperature. So you have to have a temperature difference for the heat to transfer from the hotter object to the cold object. Okay. Moment the temperatures become equal, that is heat transfer stops. Okay. That's the whole concept between this. So let's take a look at it here. And what is this? Okay, I'm going to draw this problem. I have a block. This is what 125 grams, and this is at 90 degrees. And then I'm putting this thing into a bath of water. And that has what? What's that number? How much? Oh,
20.
no, 20 degrees C. What is the rate? Mass of it? 0.326, right? Kilograms of water. 0.3. This is water. And this is at 20 degrees. So they were separate at the beginning, the block was by itself, water was by itself at different temperatures. Okay? Now you drop that block into the water. Okay? What's going to happen? Heat will transfer from the block to the water, right? And eventually they both will become the same thing. Now the block is also here, 125 gram block, and the water. All that will be at some temperature. So that temperature has to be between what and what? 90 and 20, right? Somewhere in between. Okay, it has to be less than 90, more than 20. Okay, somewhere. So if you get a value for like 100 degrees or something, you knew something you did wrong. You did something wrong. Or if you get 10 degrees C, you know you did something wrong. So that's a sanity check we like. Now, what is the mechanism? This is going to give out heat to this, right? Whatever the heat that this gives out will be absorbed by this. Okay. Hotter object is going to give out heat to the colder object. So whatever it gives out will be absorbed by this. What's the significance of in a styrofoam cup? Exactly. Heat is not getting lost. All the heat is contained in that ice bucket or whatever.
What if the top is open?
No, even top is closed.
Oh.
Wait, you said styrofoam? What did you say?
It says placed in a styrofoam cup.
So wouldn't the heat be lost in the styrofoam cup?
No, styrofoam is a fairly good conductor. A fairly good insulator. Insulate that doesn't let the heat go out. That's why some of the coolers are made of styrofoam. Okay. Like your beer coolers.
I wouldn't mind a beer right now.
No, not in this class. All right. So now what we have to do is to figure out how much heat did it give out from here. So what really happens with this object? It started with 90 degrees but ended up with what? 3 degrees, right? Which is lower than 90. What happened to the water? This water started at 20 but it went up to T. You see that? So when it dropped from 90 to T, it gave out heat. Okay? When it went from 20 to T, it gained some heat. Whatever the heat that this guy gave, water gained. Okay? So that's where the equation comes. Okay? You have to calculate how much heat did this one give from 90 to T and how much heat this one gained from 20 to T. Makes sense? That's called the heat balance. Okay? I do slightly different than the book. So what I do is I say heat given by given by the block. So I designate a letter Q out. Is the heat given out by the block. Who gains that heat? Water gains it. Okay. Heat gives out, water takes it. Okay. Q out. Yeah. So now let me write the equation for Q out. Nothing other than this. Mass times the specific heat times the temperature difference. Okay. Oh, I didn't write this thing. It's 22.4 degrees 6. So I know my thing.
Oh, yeah.
That's given. Okay. So I know that. Okay. So now what is my mass? So keep in mind, this is just for the block. Do not get confused with that. This is the heat given out by the block. Okay. The mass of the block. And so that should be now. What is the value of C we are going to use for water? Sure. Water, the C value we are going to use is going to be this value here. The book used the same value. They have used, yeah, 49. So they have used this one. So we are going to use this value here. Okay. Oops. 4186. Okay, that's what we're going to use. So that means what? Keep in mind that now you have to be careful here. This is in what? Joules per kilogram per degree C here. Okay, and but this is given in what? In grams. So I need to do what to this? I need to convert that into kilograms. Same thing with this is already given in kilograms. This is the, okay. So let's convert to kilograms. What happens now? Okay, Q out. First write the equation m times what? C times delta. And this is where I used my delta T slightly differently. My mass is going to be what? 0.125. C I do not know. I'm trying to find that. That's what the book is asking to find what C is. Okay? And delta T. So it is going to be what? 90 minus 20, 22. Usually we define delta as what? Final minus initial. If you do that, what will happen is Q out becomes negative. Because I already got the heat out, and because when I say heat out, then it's going to be a positive. Otherwise, it will be heat in. Heat in will be a negative value. Then heat out will be a positive value. So I want to have how much heat did it give out, how much heat did it absorb. So this one will, way I do my calculations, it will never have a negative value. All it tells you is how much heat did come out from the hot object, how much heat did the cold object absorb. Okay. So always my delta T will be a positive value. Otherwise, what will happen, this whole thing is going to be negative. Then I'm getting confused with, what happened to that negative sign, how I do it. Okay. That's it is like, I give some money to somebody, that person is going to be that much richer, right? I'm not going to say negative, this much I give to somebody, right? That's the whole concept. I'm looking at it from a very simplistic point. How much heat did it come out? How that heat is absorbed. Okay? So that's that amount. Now I'm going to write a heat absorbed. By what? Yeah. It will be Q in. This is what? Here this is going to be in water, right? Water bath, right? And the important thing here is to identify which one is giving out the heat, which one is absorbing. How do you figure that out? Hotter one gives the heat out, right? Colder one absorbs it. That's all. Simple. And then you know the equilibrium temperature. From there you find the temperature difference and find how much heat was given out. Then now Q in. How do I find Q in? That is equal to mass times the specific heat times delta T, right? What is the mass for the water? It's going to be 0.326. Specific heat for the water. So you have to go to say that again. 4186, right? 4186. Okay. Book has something different. Table. So this is M, then the C is going to be 4186, right? And then delta T. Now remember that it started with 20, went up to 22.4. So that's going to be 22.4 minus 20. Understand what I did? Always my delta t is going to be a positive value. Okay. If I really use the strict definition of delta, one is going to be negative, one is going to be positive. Then I will get confused with what am I going to do with the negative. That's how I avoid it.
Should we around the convert the civic heat numbers? Should we around to sig figs when we're working with it? Should we change the value at all, or just leave it?
No, just leave it like that. Okay, now we can calculate this. This will have a number. This will have an unknown c, right? So you can equate the two. Can somebody tell me? Oh, I don't need calculator. Do I? 67 that will be 60. What? 67.6. Is that right?
No, 67.
67.
Yeah.
That's right. 67.6. That one is pretty easy. 2.4, right? So now I'm going to write this. This is the most important step. Q in is equal to Q out. Why is that? Because we assume that there's no heat vector. I could give a little twist to this problem by saying this many calories went out. Then what do I have to do? Where did the calories come out of? This guy, right? This guy gave heat to the environment outside, and then rest of it went to the water. If that is the case, what do I have to do? I have to subtract. This is not the entire heat that went into the water, right? Whatever he gave to the water plus whatever went out is what came out of this. That's a little more complicated. Let's not worry about it. Q in is equal to Q out. So it's just a matter of plugging things in now. Q in is whatever this number. Can somebody work this out and tell me what that is? How much? 388? Okay. That is equal to, so what will be the units of this? Huh? Q in, yeah. Yeah, that's just a bigger number. 3275. Okay, 3270. What will be the units of this figure? Joules. Why? Your C is going to be in joules per kilogram per degree C. You see that this is kilograms, right? The meaning of that is joules per kilogram per degree C. So kilograms will cancel out with this kilogram. Your temperature difference is in centigrade. That cancels out. You are left with. Make sense? So this is 2. That should be equal to, what is the other number? You said 332? 8.44 and C. This C is the unknown. Okay. Now you calculate your C. What does it come out to be? 380. Oh, that was the answer. Okay, 388. What were the units of this? In joules per kilogram per degree C. So now you're trying to find what kind of material it is. So you go to the table and see what, 388, it is close to copper, 387 here, so that is going to be copper. You see that?
I'm sorry.
No, go ahead.
Oh, I was going to say, what pages are these on?
365. These tables are in 365. This example is on 367. This is called calorimetry. That means, heat is exchanging from one to the other. Okay?
So that's how you find the material?
Yeah. There are different ways to give this question. I can give you the starting temperature, starting mass, starting temperature, starting mass here, and specific keys for this, and ask you to find what's the final temperature. In that case, you take it to be T. There will be a T here. There will be a T here. You solve it. Okay. The different ways.
So this is a more complex version probably of the I remember when I was going to military, asking questions like this about like
Yeah, don't lose 5 coins.
Yeah.
And you had to pump
Yeah,
the
for
water,
that,
and you
it's
got
already
another bucket of water.
Yeah, a hot water.
Yeah, yeah. And then
When you mix
how
it,
much-
you know what I mean,
how much
it
would
will
it
be
take?
less than the hot one
This is
and
more
mix
difficult.
that.
This is more difficult, right?
Yeah. Because they are, your C is going to be the same as water. Okay. Here there are two different C's. One for one metal and one water.
Okay, that's great. Can't wait to learn.